Students, welcome back. In previous lecture we studied about Lenz law and motional EMF. We have seen that there are three methods of producing induced EMF in a coil. First it was by changing the magnetic field intensity. Second it was by changing the area exposed in the magnetic field, area of the coil, by changing the area of the coil. And third one now here we have by changing the orientation of the coil in magnetic field. Let us start. We can see that there are uniform magnetic field lines directed rightwards, and in uniform field a coil is placed here, and the plane of the coil is exactly perpendicular to the magnetic field lines. Therefore, maximum number of lines are passing in the orientation shown here. Now, if we rotate the coil, let us see. If the coil is rotated by small angle, then we can see that now the less number of lines are passing perpendicularly through the coil. If we further rotate the coil by more angle, then the plane of the coil becomes parallel to magnetic field, and magnetic field lines do not pass through that coil. So we can see that if we rotate the coil in magnetic field, if we change the orientation of the coil, then magnetic flux linked with the coil can be changed, and by changing the magnetic field we know that the induced EMF can be generated in the coil. So let this, the coil is PQRS is the coil, and it is placed in magnetic field, and it is being rotated by angular velocity omega. Let this is the direction of normal of the coil. This is the direction of normal, such that the angle between normal of the coil and magnetic field is theta. Theta is angle between magnetic field and normal. Now in this situation, what is the flux passing through the coil? Flux, we know that it is BA cos theta. It is B into B magnetic field, A area of the coil, and cos theta. Theta is angle between normal of the coil and magnetic field. And if there are n number of turns, suppose there are n number of turns, in that case the total flux linked with the coil will be NBA cos theta. So this is the flux linked with the coil. Now suppose the coil is rotated with angular frequency or angular velocity omega. In that case, omega, we know that it is angular rotation divided by time taken, means omega is equal to theta divided by t. Here small t is the time taken for rotating the coil by an angle theta. Then theta will be equal to angular velocity multiplied by time. So we can replace theta by omega t here. Then the expression becomes phi is equal to NBA cos omega t, because in place of theta we have written omega t here. Now as we are rotating the coil continuously, means the coil is rotated uniformly continuously in the magnetic field. So for obtaining the induced EMF we can differentiate the expression of phi with respect to time. So differentiating with respect to t, we get d phi by dt, that will be equal to NBA. It is constant, it remains as such, and derivative of cos omega t, it is differentiation of cos is minus sine, therefore negative sign appears here. Differentiation of cos is minus sine and omega t, and the differentiation of omega t is omega. So the differentiation of phi with respect to t is minus NBA omega sine omega t. Now induced EMF is negative of d phi by dt, so we put one more negative sign here, then it becomes minus becomes positive, so it becomes NBA omega sine omega t. So this is the expression for induced EMF, NBA omega sine omega t. So if we replace this NBA omega by the maximum EMF E naught, here NBA omega can be replaced by E naught. E naught is maximum EMF induced in the coil, then E is equal to E naught sine omega t. So this is the expression for induced EMF. Because the coil is rotated continuously, so induced EMF is also dependent upon time, and it is varying sinusoidally. At some instant the EMF becomes maximum when omega t is 90 degree, then becomes 0 when omega t is 0 or pi, 2 pi, 3 pi, 4 pi, means integral multiple of pi, then in that case E becomes 0, and induced EMF becomes maximum when omega t angle is odd multiple of pi by 2, 3 pi by 2, 5 pi by 2. In that case induced EMF becomes maximum. So This is the method of producing EMF, induced EMF in a coil by changing orientation of the coil. So if we plot a graph between induced EMF and angular position of the coil, if theta is integral multiple of pi by 2, 2 pi by 2, 3 pi by 2, 4 pi by 2, 5 pi by 2, 6 pi by 2, and so on, then in that case the EMF induced in the coil changes, and EMF induced in the coil changes. So let us see what will be the graph in that case. On y-axis we have EMF, then the variation of EMF with respect to time will be like this, because we have seen that E is equal to E naught sin omega t. So variation of EMF is sinusoidally with respect to time. So the graph of sine will appear here, and the graph of sine looks like this. So this is the variation of induced EMF when a coil is rotated in magnetic field. So we have discussed this, when it is maximum, when it is minimum. So if initially at time is equal to 0, the coil was not perpendicular to the magnetic field, the coil was parallel to magnetic field. In that case the differentiation becomes E is equal to E naught sin omega t cos omega t, and the variation looks like this. So if this is the case, if initial position of the coil is taken at 0 degree, that is normal to the coil, then in that case if we add theta plus pi by 2, means in previous case we have taken that theta is equal to 0 degree. In this situation the theta was 0. In this situation, if theta is taken 0 degree, then the expression is NBA, expression for EMF will be E naught sin omega t, and if theta is 90 degree, then the expression of EMF will be E naught cos omega t, and the variation will be according to cosine. Like this. So next we have very important topic, that is eddy currents or Foucault currents. Dear students, eddy currents are induced currents, and these are induced when a metallic substance like copper, iron, aluminium, any metallic substance is exposed to changing magnetic field. When a metallic substance is placed in changing magnetic field, then circulatory currents are induced in that metal, and those circulatory currents are known as eddy currents. So you can see definition: induced circulatory currents produced in solid metal due to change in magnetic field in the metal, these are known as eddy current. Means you have a metal, you placed in magnetic field and change the magnetic field, then the currents are induced, and those currents are circulatory currents are induced in metal, and these currents are known as eddy currents. You can see this is a metallic block placed in non-uniform magnetic field is changing in direction as well as in magnitude. So in that case circulatory currents are produced, and these are eddy currents. Now application, these eddy currents are very very important, and these have found many applications in daily life. Some of the applications are discussed here. Number 1, induced in induction furnaces. Dear students, in industries induction furnaces are used. Induction furnaces are such that a large crucible or large bowl is there, and coils are wound at the bottom and on the walls of that container, and those coils are given alternating current. And if we put metal in that bowl and alternating currents are given to that to those coils, then eddy currents are induced in metal, and because of eddy currents a large amount of heat is produced in metal, and the metal comes to molten state. So that is the induction furnace. You can search on internet the functioning of induction furnaces. You will easily get some videos to visualize what happens in case of induction furnaces. Okay. Next we have in speedometer, eddy currents are used to measure the instantaneous speed of the vehicle. In speedometers, those are in all vehicles, in bikes, cars, everywhere. The speedometers are there, and those speedometer works on the basis of eddy currents. When the wheel of the vehicle is rotating, then the metallic block in the wheel cuts the magnetic field lines, and those magnetic field lines are because of earth's magnetic field lines are cut by the rotating vehicle. So eddy currents are produced, and those eddy currents are used to represent the instantaneous speed of the vehicle. Next, in deadbeat galvanometer, eddy currents are used to stop the damping of the coil in short interval. Dear students, galvanometer is a device which is used to represent that current is flowing or not flowing in a circuit. Suppose we give the current to a galvanometer, then the needle of the galvanometer suddenly goes to the maximum, and suppose we remove the current, then the needle will suddenly come back to the initial position. In that case, because of sudden forces, the unwanted oscillations are produced in the coil of the galvanometer. These unwanted oscillations can be removed with the help of eddy currents. Suppose the coil of the galvanometer is wound over iron or some metallic block. Then in that case, if we suddenly give the current to galvanometer, then the current increases in galvanometer, and because of increase in current, the eddy currents are produced in the coil of galvanometer, and those eddy currents would oppose the rise of the current in galvanometer, and because of opposition offered by that eddy current, the needle of the coil will not suddenly go to the maximum and will not suddenly come back to the initial position, and unwanted oscillations of the coil can be avoided. So let us see fourth application. In electric brakes of trains, eddy currents are used to stop the rotation of the axle of the wheel. So electric brakes, you might have seen. In disc brakes, you see in many bikes disc brakes are coming, in many cars disc brakes are coming. Those disc brakes works on the principle of eddy currents. In case of disc brake, a disc is mounted on the side of the wheel of the vehicle. When the wheel is rotating, then those eddy currents are produced when we apply the brakes, because when applying brakes, the current passes through a coil, and those coil, the magnetic field is produced in the coil, and that magnetic field lines are cut by the rotating disc, and eddy currents are produced in disc, and because of eddy currents, the eddy current opposes the motion of the wheel, and brakes are automatically applied. You can read the detail of this topic at details of electric brakes, detail of deadbeat galvanometer, details of speedometer, induction furnaces on internet. These are easily available on internet. So for CBSE exam, you just need to remember that what are the applications of eddy current. You need not to go into the depth of these topics, because these are directly not into your syllabus. Only the concept that you should know, that what concept is there. In energy meter, eddy currents are used to measure the consumption of electricity. Dear students, we have energy meters in our homes. When the electricity supply comes to our home, then first it enters into the energy meter, and there is a disc in the ring in the disc or ring in the energy meter, which rotates because of eddy currents induced. The more the quantity of current enters into our house, the more eddy currents are induced, and more energy meter moves. Therefore, it represents the energy consumed. Next we have, in diathermy, eddy currents are used for localized heating of tissues in human body. Okay. Next topic is self-induction. Dear students, we have two more topics, self-induction and mutual induction. We will cover these topics in our next lecture. Till then, thank you very much.